Hello guys, this is Dev. Today we are going to continue with the second part of simple harmonic motion. Okay, so let's start. Alright, so first topic is simple pendulum as simple harmonic oscillator. Okay, in the last video we saw that the spring could behave as a simple harmonic oscillator. Now here I want to show you the pendulum can also behave like a simple harmonic oscillator when displaced with a very small angle theta. Okay, I am assuming theta is small. Okay, this is the first assumption that I have made, that theta is small. Now for example, if I have displaced this ball of mass m and now I leave this ball, then what happens is this ball goes in the direction, for example, if this is positive and this is negative x, this is positive y and this is negative y. Alright, and it goes up till here and then comes back and keeps repeating this motion. Okay, so this has been converted into a simple harmonic oscillator. Now generally questions are asked to find the time period of this oscillator. Okay, so I'm going to show you how we derive it. For example, if the ball is taken over here, this point A, for example, let us say is the maximum position. Okay, so here the velocity will be 0 because it is the maximum position. So here only acceleration will act. So what are the forces on ball? Now I want to see the forces acting on the ball. First is the tension due to the string. Next is the weight. Okay. Are there any other forces? No. There are no other forces. Air resistance is not there. Air resistance is not there. Okay. So how now the ball is not going this side. Okay, it is accelerating this side. This means the tension must be balanced by some force. So it can be balanced by the component of the weight. So if this tension makes an angle theta here with the vertical, this means since these two are parallel lines, the gravity will also make an angle theta with the line of tension. Okay, so this component becomes mg cos theta and this component becomes mg sin theta. So T balances with mg cos theta. Okay, so no problem over here. And the ball is going in the negative x direction. This means that the acceleration now would be minus mg sin theta. This would be equal to ma. Okay, here we have the acceleration. Gets cancelled out. A is what? D square x by dt square. If we assume displacement to be x, this would be equal to minus g of sin theta. G times sin theta, sorry. So for a very small angle, what happens is sin theta becomes theta, alright, and cos theta becomes 1 minus theta square, or we can say 1. For a very small angle, sin theta reaches theta and cos theta reaches 1. You should know this. Okay, so for a very small angle, if this displacement is x and this length is L, sin theta would be the perpendicular by hypotenuse. This means x by L, right? So we can write this as minus g times x by L. Okay, so I am bringing this expression to the left hand side. This we have d square x by dt square plus g x by L to be 0. Okay, now whatever be the displacement, I am not concerned with it. I only want to find out time. Okay, so generally what happens is, so we have the equation d square x by dt square plus g by L x to be 0. Okay, so now I assume this g by L to be omega square. So we have d square x by dt square plus omega square x to be 0, and this omega is the angular frequency. Okay, this omega in simple harmonic motion, as I earlier told you, was the angular frequency. So omega was root g by L over here. Now we can find out the time period with this angular frequency. This would be 2 pi by omega. Okay, so this would be equal to, time period would be equal to 2 pi root L over g. This is my answer. Okay, because you know omega is 2 pi f. F is the frequency and this omega is the angular frequency. So f normal is 1 by t. Alright, so 2 pi by t is omega. So here t is equal to 2 pi root L by g. This is my answer. We can use this formula for n number of purposes as we use them, and we arrive at this formula. This is very important. Okay. Now we will study the composition of simple harmonic motions. For example, if there is a particle, there are two forces F1, F2 acting on this. F1 produces a simple harmonic displacement of x1, let us say A sine omega t, okay, A1. And the F2 produces x2 equal to A2 sine of, let us say, omega t plus phi. Phi is the phase here, okay. Phi will distinguish these two motions, and because these two are different forces, so different S.H.M will be produced. Now both these are along x directions, okay. So we want to find out and you see the frequency is also same. So we have to find out the resultant position of this particle, resultant amplitude, resultant equation of the displacement, okay. So how do we do it? We just sum up, okay, these two, x1 plus x2. We get the net displacement x, which would be A1 sine omega t plus A2 sine omega t plus phi, okay. This will be the net displacement at any given point of time t, okay. Right now this is not the amplitude, okay, because amplitude is the maximum of this. This is the net displacement at any time, okay. So we just now open this, A1 sine omega t plus A2 sine A cos B plus A2 cos A sine B, right? Alright, so we have A1 plus A2 cos of phi times sine omega t plus A2 sine of phi cos omega t. Alright, this is the final displacement as a function of time, not the amplitude, okay. So we had the final displacement as A1 plus A2 cos phi sine omega t plus A2 sine phi cos omega t. Alright. So we can write this expressions as, we can take this term as D, we can take this term as E. Alright. So we can write this expression as D sine omega t plus E cos omega t. Alright. We can take x this. So what we now can do here is, we can simplify and we can, obtain one equation from this. For example, this is D sine omega t plus E cos omega t. So what we can do this, we can multiply and divide by root under d square plus e square. Alright. This would give us d upon root under d square plus e square sine omega t plus e upon root under d square plus e square cos omega t. Okay. So we can assume tan alpha. Okay. We can assume tan alpha, for example, we can assume this as E upon D. Alright. So if tan alpha is E upon D, what is sin alpha? Sin alpha will be E upon root under D square plus E square. And what will be cos alpha? Cos alpha will be D upon root under E square plus D square. So we can reduce this equation in the form of as root D square plus E square times D upon this, which means sin omega t cos alpha plus cos omega t sin alpha, right? Sin a cos b plus cos a sin b is sin of a plus b. This means this will be sin of omega t plus alpha root under d square plus e square. Now we have a composite equation of this, okay? So we have x equal to root under d square plus e square sin of omega t plus alpha. This is the composite equation now. So you see the net amplitude, this is the amplitude. Why? Because if I take x max, sine would be 1, because modulus of sine, sine maximum value of sine is 1. So x max will be the amplitude. As I told you earlier, this would be root under d square plus e square. Alright. This would be the expression of the amplitude. Now what was amplitude? D was A1 plus A2 cos of phi. whole square plus what was E? E was A2 sine phi. I think I'm correct in this. Okay. Now we have to just square them up and sum them. We have A1 square plus A2 square cos square phi plus 2A1 A2 cos phi plus A2 square sine square phi, right? So this is A. A is the amplitude. This is the maximum amplitude one can achieve, or we can say this is the maximum displacement one can achieve. So this would be root under A1 square plus A2 square plus 2A1 A2 cos of phi. Alright. A was root under A1 square plus A2 square plus 2A1 A2 cos of phi. Okay. Sin alpha was E upon root under E square plus D square. Cos alpha was this. What will be tan alpha now? Tan alpha would be D over E. Okay. And what will be this? This would be A2 cos of phi upon A1 plus A2 sin. No, A1 plus A2. Sorry. This was A2 sin phi. Yeah. A2 sin phi upon A1 plus A2 cos of phi. Okay. This is the answer. So, questions can come. They can give you two displacements x1 and x2. And they can tell you to find out the phase lag between them, and also they can tell you to find out the net amplitude, which is this. Okay, net amplitude will be this if there is a composite simple harmonic motion, and the net phase would be alpha would be tan inverse of this. Okay, so questions like this do come, so you have to be prepared with this. Okay, so now we talk about composite S.H.M in perpendicular directions. Okay, earlier we did was the same direction, x1, x2, same axis, same direction. Okay, but now what do we do in composite S.H.M? Composite S.H.M means, for example, x let us say is A1 sine omega t, and y let us say is A2 sine omega t plus phi. Now this is y. Okay, this is y. You cannot simply add it. X plus y cannot be done. This is wrong. Okay, this will be straight away wrong because this is y. This is not the same axis. Alright, so how do you do this? So what we can do here is we can substitute sine omega t as x by a. Okay, and we can substitute the value of sine omega t here. So y we have a sine omega t cos phi plus this was a2. Okay, a2 cos omega t sine phi. So y will be equal to a2 times what is sine omega t, x upon a times cos of phi. Okay, and plus a2 what was cos omega t. Now cos omega t will be equal to under root 1 minus x square by a square. Okay, so this will be root under 1 minus x square by a square, and this would be sine phi. Alright, let me write it again. Y was a2 times this would be x by a1 cos phi plus under root 1 minus x square by a1 square sine phi. Okay, alright, so now what should we do here? What we can do is we can take a2 over here, so we have y upon a2. Alright, we can take this expression on the left hand side, we have x upon a1 cos of phi, and we can square it up. So we have 1 minus x square by a1 square, and this would be sine square phi. Okay, so we open this, we have y upon a2 whole square plus x upon a1 cos square phi minus 2yx by a1 a2. This would be cos of phi, and the right hand side would be sine square phi minus x square by a1 square sine square phi. We can take this expression on the left hand side and add it up to this. We have y upon a2 square plus x upon a1. Okay, this would be square also, a1 whole square minus 2yx upon a1 a2 cos phi, this would be equal to sine square phi. Alright, so this is my final equation. Okay, so the final equation is y upon a2 whole square plus x upon a1 whole square, alright, minus 2xy cos of phi upon a1 a2, this would be equal to sine square of phi. Alright, this is my final equation. Now what type of oscillation will take place depends on phi. We can take special cases. For example, let us say phi to be 0. If there is no phase lag between them, what happens is sine 0 becomes 0, cos 0 is 1. So we are left with y upon a2 whole square plus x upon a1 whole square minus 2xy upon a1 a2. So this would be 0. Okay, so simply this means y by a2 minus x by a1 whole square. So we have y equal to a2 by a1 x. Alright, y equal to a2 by a1 x. So what is the graph of y equal to x? Graph of y equal to x is like this. Alright, since this is on the positive side, this means if this is negative, x will also be negative. So these will be in first and third quadrant. Okay, so this graph is correct. An oscillation will take place like this. First particle will go here and then come back and then go here and then come back. Okay, so this is the this is the oscillation the particle is doing when y equal to a2 by a1 x, or we can say when phi equal to 0. There is no phase lag. Okay, this is in 2-dimension composite simple harmonic motion. Okay, now y upon a2 whole square plus x upon a1 whole square minus 2xy by a1 a2 cos of phi was sine square phi. Okay, so let us say phi to be pi. Now what happens when phi equal to pi? Sine pi is 0, but cos pi is minus 1. So what we are left with? We are left with y by a2 plus x by a1 whole square. Okay, to be 0, because this will become plus. Okay, so we are left with y equal to minus a2 by a1 x. So you see how the oscillation will change now. The oscillation will be like this. The oscillation will be in second and fourth quadrant, because if one will be negative, the other will be positive. Okay, so this will be the oscillation. First particle will go here, come back, and then go here and then come back. Okay, suppose we say that phi to be pi over 2. Now what happens? If phi is pi over 2, this would be 1 and this would be 0. So we are left with y upon a2 whole square plus x upon a1 whole square to be 1. Okay, this is the equation of ellipse. If you recall, x by a whole square plus y by b whole square to be 1. This is 1. Okay, so this is an equation of ellipse. So the particle will travel in an ellipse. Okay, that particle will go like this. The motion, simple harmonic motion described by the particle would be in the form of ellipse. Okay, the components would be going back and forth along x and y axis, but the whole particle will be traveling along an ellipse. Okay, and this is an ellipse, and for example, this would be positive a1, this would be negative a1, this would be positive a2, and this would be negative a2. What if a1 was equal to a2 equal to a? Then if phi would be equal to pi by 2, then the equation was y square plus x square equal to a square. Hence the particle would be going in a circle, not an ellipse. Okay, this would be a, this would be a, this would be minus a, and this would be minus a. This would have been a circle. Individual components would be traveling along both the axes, and this would be a circle. Okay, so questions like this are asked more often. Okay, for example, they will give you a phase phi equal to pi and give 4 options, 1 2 3 4. What is it? Ellipse hai, what is if circle, parabola, whatever. You have to mark the correct answer. Okay, alright, so we now move on to torsional pendulum. What happens is, here is there is a string and there is a disc attached. Okay, This is a classic case of angular simple harmonic motion. Okay, just remember it is not linear. Okay, it is angular simple harmonic motion. This wire remains fixed here, but this end, lower end of the wire can be rotated. So when we rotate it, the upper end tries to, resist the rotation and brings it back to the original position. So when you rotate the wire should be, brought back to the original position. So in this case, the torque exerted is proportional to the angular displacement. Okay, since the torque is exerted in the opposite direction, or we can say the angular displacement is in the opposite direction of the torque, because angular displacement is in, for example, anti-clockwise direction over here, but the wire will exert the torque in the clockwise direction, because it is a restoring torque. It has to bring the torsion back. So torque is proportional to the angular displacement. So in general, we write this as k minus k theta. Okay. Again, I am telling, if I have displaced the disc, for example, if I have rotated the disc in the anti-clockwise direction, the string will bring the disc to the original position, back to the original position. So if the displacement is positive, the torque should be negative. Okay, it will be exerted on the negative side so as to bring the disc in its original position. So torque is minus k theta over here. In general, what happens is torque is I alpha. So this would be equal to minus k theta. I is the moment of inertia of disc. Okay, so alpha is minus k by I times theta. Alpha in rotation, you see, omega in rotation, as I told you earlier, was d theta by dt. Alpha is nothing but d omega by dt. This would be equal to d square theta by dt square. It is same as in kinematics. Just v is replaced by omega, acceleration is replaced by alpha, and displacement is replaced by theta. Okay, only difference is this. This is linear and this is rotational motion. Okay, so alpha would be d square theta by dt square. We can take this expression on this side. So we have d square theta by dt square plus k by I theta. This would be 0. Okay, so this is again a simple harmonic motion, and this is a S.H.M equation. So I assume k by I is omega square. So we have d square theta by dt square plus omega square theta to be 0. So omega would be equal to root under k by I, and the time period we can calculate would be 2 pi by omega. This means 2 pi root I by k. In general, if we try to solve this equation, we will get theta equal to some amplitude theta naught sine of omega t plus, let us say, del. This is the phase. Okay, just assume this is phase, nothing much to do over here. This is the answer. Okay, the answer for time period of torsional pendulum is 2 pi root I by k, where k is the stiffness of the torsional pendulum and I is the moment of inertia of the disc, or whatever it is attached to, whatever the thread of the torsional pendulum is attached to. Okay, so this was the equation of torsional pendulum. This is theta naught sine omega f t plus whatever it is, and this is the torque and this is the time period. Now I want to find out the total energy. Now how do I do it? First of all, total energy will consist of two things. You see, if the torque is produced in the negative direction, it will contribute to potential energy because it is resisting the motion, and the object, whatever of moment of inertia has been rotated. This means this will consist of, first of all, potential energy due to torque, okay, and kinetic energy, or we can say rotational energy. I want to say rotational energy due to object. Okay, so this will be the total energy. Now what is the potential energy due to torque? For example, the work done due to torque would be tau d theta, as everyone knows. This would be minus k theta d theta, and we can integrate this. But you see, this is the work done, this is not the potential energy. Work done is negative of potential energy. So minus minus will be cancelled. So u will be equal to half k theta square. Okay, and what is the rotational energy due to object? This would be half I omega square. Okay, as everyone knows, in rotation it is half I omega square. Okay, so the total energy, now this becomes et, this is u. Okay, Half k theta square is u, and this is rotational energy. Now let us find out. You see, this actually this omega is not to be confused with this, because this is the angular velocity. Okay, so what is the angular velocity? Since the angular displacement is this, we can just differentiate this. This would be d theta by dt. That's why I've written omega f to separate it from omega. Okay, this would be, what will be d theta by dt? This would be omega. Okay, this would be omega. So this will be theta naught omega f cos of omega ft plus del. All right, this would be the omega. Now omega square, what was omega square? This was k over I, right? So k is I omega square, as we know. So half k theta square will become half I omega square, and this will be theta square, plus half I omega, this is omega f. Okay, omega f, and this is omega. Omega f is angular frequency, this is the angular velocity. These two things are different. Okay, these two things are different. So what is now what is theta? Theta was half I omega f square. We can write this. Theta was theta naught square sine square omega f t plus del, right? Now half I, what was omega? Omega was d theta by dt. This was theta naught omega f cos of omega ft plus del, right? So we can square it up. We have half I theta naught square omega f square cos square omega ft plus del. So we can take this common, half I omega f square theta naught square, we can take this common. So we have half I omega f square theta naught square into sine square x plus cos square x is 1. This is the total energy. You see, this energy is constant. This energy total is constant, half I omega f square theta naught square. This is the answer. This means this is a conservative force acting here. Obviously in S.H.M conservative force acts, so energy is conserved, conservative force is acting. Alright, so moving on, I have another method for pendulum, and we can do this through angular S.H.M. Okay, since mass is rotating here about point O, let us say this is point O and this is point P. So you see, this is the angular S.H.M because the mass is rotating. Alright, now I want to find out the time period. How do I do it? First of all, we can see this is rotating, and because it is rotating, this means a torque must be generated. Tension cannot produce this torque. Why? Because it is along the line joining O and M, and torque is obviously R cross F, which is RF sine phi. Phi is the angle between R and F. But here, if we take tension into account, L and T have the angle 0, or we can say 180, because obviously 0 or 180 either ways will give torque as 0. So the only other force would be mg. Mg has two components, one in this direction and one in this direction. So this would be mg sine theta and mg cos theta. Mg cos theta, again you see, is along the line of tension. So mg cos theta will not produce torque, won't produce torque. Okay, only mg sine theta will, and mg sine theta is 90 degrees with L. This means torque will be equal to minus mg sine theta times L sine 90, which is obviously 1. Why am I putting minus sign? Because you know, this torque brings back the particle to this point P. For example, if I have displaced this particle along this line and I have left the particle, it is coming back. Again, when it goes over here to the other extreme, it tries to come back. Okay, so this means the torque is bringing back the particle. So that is why the torque is negative. So torque is I alpha. As I earlier told you, this would be minus mg sine theta L. Alright. Now you see, because you know, theta is very small. As I earlier told you in the simple pendulum, and theta is small, sine theta is approximately theta. So I am writing this as minus mg theta L. Okay. Alpha would be equal to minus mg theta L by I. What is I? I is the moment of inertia. But how do we calculate it? It is summation mr square. What is the moment of inertia here? It is m times L square. Because rotation is about 0.0. Rotation is about 0.0. So I would be equal to m L square. Okay. This would be minus mg L theta by ml square. Gets cancelled, LL gets cancelled. So alpha is what? Minus G by L theta. Okay. Alright. Alpha is minus G by L theta. What is alpha? Alpha is d square theta by dt square plus G by L theta. This is 0. We can assume omega to be root G by L. And what was T? T would be 2 pi by omega. So T would turn out to be 2 pi root L by G, which is the same as I did earlier. So this is the answer. Okay. Alright guys, I'm stopping here. We'll continue with the problems of simple harmonic motion, and then we'll move on to other topics like fluid mechanics and then optics. Okay. Please like, rate, review, subscribe and recommend. Thank you.